Understanding the share buffers. When there are thousands of users trying to read or write data to many different tables, reading from files will result in a poor, non-scalable system. The read and write will result in searching for many files, opening these files, looking for specific data records, locking, editing, and unlocking. To make this a lot more scalable and faster, the concept of share buffer is introduced. Now, the backend processes are no longer reading from the files and writing to the files, but rather dealing with buffers or RAM with a significant improvement in performance. The amount of memory to be allocated is decided by the share buffer parameter in PostgreSQL configuration file. The fixed size block of share memory is allocated when the server is started. It's not this memory chunk alone that is responsible for improving the response time, but the operating system cache also helps quite a bit by keeping a lot of data ready to serve. Together, these two caches result in a significant reduction in the actual number and volume of physical reads and writes. In addition to these two levels of caching, there could be a disk controller cache, disk drive cache, and so on. The bottom line is that these caches improve performance by reducing the physical necessary I/O. There is also a risk associated with huge caches, such as spikes in I/O when large volumes of data get flushed from the buffer to disk. Let's consider the possible routes a simple select statement might take considering the share buffer cache and the operating system cache alone. The first thing the process will check is whether the data it wants is available in the database buffer cache. If it's not available in the database buffer cache, a request goes to the operating system to fetch the specific file or block. There is a chance that the operating system cache already has the file or block and passes it to the database cache. In both cases, a physical I/O is avoided. It's only when the data is not present in either of these caches that a user read or write request will actually result in a physical I/O. It's obvious that most of the data fetch and written happens via buffers. Exception to this would be databases where the buffer is tiny compared to the data that it's usually read and written. Even in cases where the number of queries per second is very high, the physical I/O will be limited if these transactions are mostly working with the same datasets. However, if transactions are occurring in really different areas of the file system, then we might still get frequent flashes to disk.